Akshita, am I audible?
Yes, ma'am. Can you hear me, ma'am?
Yeah. Am I audible to you?
Yes, ma'am.
Fine. So let's continue. We were on E4 topic where we have discussed the minimum mass required for a chain reaction,
Yes,
which is called its critical mass. Done. So today we have to
yes, ma'am.
start with a nuclear reactor new topic. Fine?
Yes, ma'am.
Yeah. Will you continue with the classes
Yes, ma'am.
and tell me your schedule?
I'm planning to do like what is it? Alternate days classes, ma'am, because I also have like a computer science exam coming up, which I have to do past papers. Like so like we will have tomorrow like 23, 24, 25, 26, 23, 25, 27.
23,
Like,
25, and then?
and then I have my
And
27.
you have your physics exam is on 29th, right?
Yes, ma'am.
Yeah. So 29th already the exam is there. So now you are taking on alternate days.
Yes.
Fine.
Because after that, I don't have time for computer science. Like, uh, I have like a continuous exam. So that's why.
Okay. Okay. Just do let me know about your schedule. Like today you will take, so then tomorrow you will not going to
Yes,
take,
ma'am.
right?
Yes, ma'am.
Then day after tomorrow
I will like.
you will take. So day after
No,
tomorrow
ma'am.
you will
Once
going to
again,
take the class.
I once again, once again.
Am I audible?
Hello, ma'am. Can you hear me?
Yeah.
Yes, ma'am. Uh, yes, ma'am. So like Tuesday, Wednesday, Thursday. If is it possible if we can have like a class earlier tomorrow, ma'am? If not, we can have from Thursday, Saturday, and then Monday.
Give me a sec. Just give me a sec. I'm telling you your schedule. So tomorrow you don't want the class, right?
Yes, ma'am.
Okay. And again, day after tomorrow, you want to have the class. That is on Thursday, you will take the class.
Yes, ma'am.
Okay. Then Friday?
No, ma'am.
Friday, no.
And
Saturday?
Saturday I will have a class.
Saturday, you will take the class. Okay.
Yes.
How about Sunday and Monday?
Is it okay if we can have the Monday's class, like the third class on Sunday, ma'am? Because before the exam, I will be like little nervous, so I will just take some time to just review like the notes alone. So I don't want to have any class on the day before the exam.
Okay.
So
So you want to have the class on
is it
Sunday?
okay if we can have Thursday, Saturday, Sunday? Yes, ma'am.
Okay. Sunday at what time?
Uh, Morning 11, ma'am.
Okay. Fine. Let me plan it and I'll tell it to you. Done? So tomorrow no
Yes, ma'am.
class, Thursday is a class, Saturday is a class, and Sunday is a class. Right?
Ye- yes, ma'am.
Thursday, Saturday, Sunday in this week. Done?
Yes, ma'am.
And after that, like after the exam, you will discontinue the class, right? After Sunday.
Yes, ma'am. If possible, I can try taking a class uh on 29th, like the evening. Since my school is far away, so I have to, like, when I reach home, I will I will just message you if I have time. And if you
For sure.
are available, then we can pause it on class
Okay.
on
Fine.
29th of each.
Okay.
Okay, ma'am.
Fine, Akshat.
Yes, ma'am.
No issue on that.
No, ma'am.
So, yeah. Let me explain you now nuclear reactor.
Yes.
Okay. So, check very carefully. Okay, understood.
Yes, ma'am.
Akshita, nuclear reactor that
Hello, ma'am.
was. Yeah, am I audible?
Yes, ma'am. Yes, ma'am.
Fine. So now after this, let's continue. Normal topics in this. First one is nuclear power. So just listen very carefully. When a large nucleus splits into two smaller nuclei, the total binding energy increases. Okay, this results in the release of 100 MeV of the energy. Okay, so approximately 100 million times of the more energy releases per molecule when the coal burns. Okay, so any material what does this could be valuable source of energy. Understood? So
Yes,
uranium
ma'am.
235 nucleus absorb a neutron and it will undergo fission reaction. And normally the uranium contains 0.7% of the energy of 30 U35. Fine. So the remainder is uranium 238, which basically absorbs the neutron and without undergoing fission before naturally occurring uranium basically used as a fuel. Understood? So the amount of uranium
Yes,
235 energy releases is increases by 3%, which is called enrichment. Okay? Understood?
yes, ma'am.
Yeah.
Yes,
Usually a uranium fuel releases 1534 million amounts of okay. So 1534 million megajoules per liter of the energy is released via uranium atom. Okay. And it increases by 3% when it absorbs neutrons. Done? Now after this,
yes, ma'am.
the chain reaction. So in the last class also I had told you that what is chain reaction. Basically what happens is uranium 235 splits and it requires some more energy because the nucleons are held together by a very strong force. So for this we react it with neutrons. We react it with neutrons and hence you will get barium and krypton plus the release of three more neutrons which again collide with more three uranium 235 and hence it is known as the chain reaction. Understood, Akshita?
Yes, ma'am.
Okay. So basically this reduces the stability of the nucleus. So it splits into two and hence there are too many neutrons for the smaller daughter nuclei and they are released. So these neutrons can be captured with more uranium 235 to produce the chain reaction. Understood? Now after this we are having the third component which is very important in this and that is known as moderator. Okay, let's have a look what is moderator. So neutrons will only be absorbed if they are traveling slowly. Okay, what happens is your neutrons, you had seen it in the diagram also, no? In the working.
Yes,
It should travel slow. So that it absorbs slowly. Then otherwise it will straightly pass through it and it will not collide with the uranium atoms. Okay, so basically in terms of kinetic energy this would only be about nearly 1 electron volt. Okay, it's kinetic energy I'm telling. Done. which is much less than the mega electron volt energy, and hence they possess after being expelled during the fusion process. So to achieve this chain reaction, we need to have these neutrons to be absorbed so that they can be slowed down or moderated. Done. So this is done by introducing some small nuclei between uranium-235. Okay. Water is sometimes used as a moderator because it contains, yeah.
I think I lost internet and I get kind of rejoined. So can you like just explain the moderator part once again, like?
Okay. Now is it audible clearly?
Yes, ma'am.
Okay. So I'm saying in the moderator, the neutrons will only be absorbed if they are traveling very, very slowly. And hence we are using moderator for this. That is water. Okay. So when they collide with the water molecules, they slow down and they moderate. Then because generally they have an energy of 1 electron volt, which is very much less than mega electron volts of the energies. Then
Yes, ma'am.
okay. Now, why we use water? Water is sometimes used as the moderator because it contains the hydrogen nuclei and the neutrons collide with these nuclei. Okay. Because they have a very similar mass to that of the neutrons. Correct. So to receive the energy, the neutrons slow down and nearly a elastic collision occurs. Done?
Yes, ma'am.
And hence it moderates down. Fine. So now after this, the third very important pointer in your nuclear reactor is, I had told you to watch the video of nuclear reactor. Have you?
Nuclear reactors, they
You
control
need to.
the.
Whenever I'm giving some work, you need to do it. Otherwise, it becomes very tough for me that how you will attend all the things.
Ma'am, it connects the like it kind of releases energy like the nuclear fission releases energy and then the energy will and the I think the coolant will produce uh, once again, ma'am.
Yeah, say.
The coolant will produce like hot particles and then that will be absorbed by uh, the
Mm-hmm.
some like and at the end like the electricity is produced from the generator.
Yeah, exactly. From the nuclear energy, we are releasing the electrical energy. So it behaves like that.
Yes, ma'am.
Okay. Yeah, fine. So let's come back to the topic again. So what I was telling is critical mass. So another factor, very critical factor that determines whether the chain reaction can be take place or not, that is the size of the piece of the uranium atom. Okay. So if it is very, very small, then before the neutrons have traveled far enough to be slowed down, they will have left the reacting piece of the uranium. Okay. So the minimum mass required for the chain reaction is known as the critical masses. Okay. So they do not need to be very, very small. So what do we do with that? We basically let it collide with some other neutrons. Okay. But I said if it is too small, then it before colliding with the neutrons have traveled far enough away to be slowed down and they have left the reacting piece of the uranium. So it will remain unreacting only. Understood? So the
Yes,
minimum
ma'am.
mass which is required is known as the critical mass. Let me
Yes,
show
ma'am.
you now the nuclear power station.
That's the place where the electricity like will be produced.
Hmm.
Power station.
Just a second, Akshita.
Okay, ma'am.
Just 1 second. I think some issue is there. Akshita, am I audible?
Yes, ma'am.
Sorry, my laptop got hanged in between and it's a technical glitch.
Okay, ma'am.
Fine. So coming back to the topic, what I was explaining is critical mass, and after that we were discussing that the mass should be high. Okay.
Yes, ma'am.
Fine. So now after this, we have nuclear power station. Let's have a look over this. What is nuclear power station?
Yes, ma'am.
Check this diagram. So basically here, we are finding one control rod. Okay. So the control rods basically control the rate of the reaction. Okay. So the rate of the reaction in the nuclear reactor is basically limited by the factor which is known as the fuel that contains a very high proportion of uranium-238. Okay. Now how does it control it? It basically absorbs. Am I audible to you?
Yes, ma'am. I can hear you.
Okay. It basically absorbs the neutron every time, and since this cannot easily be altered, it cannot be used to slow down the reaction down. Okay. So if it
Yes.
goes very, very fast, then instead this is done by introducing control rods of neutron absorbing material. Okay. Such
Yes.
as we are having boron between the fuel rods. Okay. Like you can see over here that here we are having, these are the graphites and they are the bundles of the fuel. Then here a gas is filled and the control rods are filled in between these rods. Okay.
Yes, ma'am.
Fine, Akshita.
Yes,
Okay.
ma'am.
So there are many other designs of nuclear reactor also, but they all have nuclear reaction at the core region. So this region is known as the core region. Done. Now energy is released when the nuclei split. Okay.
Yes, ma'am.
Fine. And is given the fission fragments. Done. So the temperature of the body is related to the average kinetic energy of the particles. Understood?
Yes, ma'am.
Fine. So it means that the temperature of the fuel increases and the hot fuel can then be used to boil the water. Okay. And derive a turbine as in the coal-fired power station. Understood?
Yes, ma'am.
Now, the nuclear reactor is the part that produces heat and it contains the fuel rods surrounded by, okay, graphite moderators. Can you see here that? Graphite moderators of the yellow color?
Yes, ma'am.
Okay. So the control rods can be raised and lowered down in the chamber, okay, to control the rate of reaction. Understood?
Yes, ma'am.
Okay. And now this nuclear reactor is housed in a pressure vessel, which is a gas circulating around it. So what is that? Here, you can see this gas is filled. Okay.
Yes, ma'am.
This picks up the heat from the fuel rods and transfer it to the water of heat exchanger. Understood? Over here. This picks up the heat from here and give it to heat exchanger. Can you see this black tube?
Yes, ma'am.
Okay. Okay. So it gives it to that. Therefore, in turn, the water turns into the steam and turns the turbine of the. So inside this, the water is continuously revolving around. Okay. And here are the turbines connected. What happens is this heat exchanger, here it gets the heat from this particular reaction and it gets heated up. Inside this water, cold water is filled, which gets heated up and releases steam, and steam is released on the turbines, with the help of which this turbine rotates and it gives out electricity. Understood?
Yes, ma'am.
Any doubts in this?
No, ma'am.
Okay. Now, what is a meltdown? So if the nuclear reaction is not controlled properly and suppose it got overheated and the fuel rods get melt, then this is called meltdown. Understood? So when this
Yes.
happens, the fuel cannot be removed and it may cause the pressure vessel to burst. Understood? This is the pressure vessel,
Yes.
which is containing the gas. Okay?
Yes, ma'am.
Fine. So it sends the radioactive material into the atmosphere, and the situations like have you seen that once upon in a time in 1986 in Ukraine, the Chernobyl is the place. Sorry, Chernobyl was the name of this area. Okay. And then also in Fukushima in Japan. That is in 2011. Okay. It got busted and it had created the radioactive rays in the surrounding. Okay. Which is very harmful to the people. Okay. So, however, it is not possible for a reactor to blow up as an atom bomb. Okay. Since the fuel is not of very high enough grade, so it does not give a blast. Understood? Now,
Yes, ma'am.
meltdown can be used to malfunction in the cooling system or in the leak in the pressure vessel also. So it would result into severe damage to the reactor, maybe leading to complete shutdown. Further damage outside the reactor is limited by contained or containment building. Okay, which is a airtight steel construction covered in concrete. Done. So this thorough system is covered in the concrete and steel. Understood or not?
Yes, ma'am.
Okay. Okay. So it basically prevents the leaking out of the dangerous materials and it is known as the shielding. Okay.
Yes, ma'am.
Okay. So now after this, what is the residue that we get out of it? So we get two types of residue. One is low level waste and the high level waste. Okay. So the extraction of the uranium from the ground is the process of fuel enrichment and it is transferred. Basically, the transfer of heat from the fuel rods all leave some traces of the radioactive material. Fine. It must be carefully disposed of. The amount of radiation given off by this material is not great, but it must be disposed. In some places where the human contact for 100 to 500 years is not possible. Okay?
Yes, ma'am.
The residue I am talking about, Akshita.
Yes,
Okay. So the old reactors are another form of the low level waste and they cannot be simply knocked down and recycled since most of the parts will have become radioactive. Okay. So instead they can be left untouched for many years before demolition and it can be encased in the concrete. Understood?
Yes, ma'am.
Then we have some high level waste also, Akshita. Like the biggest problem with the nuclear power industry is that the disposal of the spent fuel rods. These rods. Okay. Some of the product isotope they contain are radioactive in nature and they have a high half-life of thousands of years. Okay. So need to be placed in a safe storage for a very long time like plutonium fuel rods are considered not safe for at least 2,40,000 years. Okay, and many suggestions regarding this wastage is like something like sending it to the sun, putting it into the bottom of the sea, burying it in the ice cap, or dropping it into very deep hole. For the moment, most of it dealt within one phase, but it is stored under the water at the site of reactor for several years to cool off, and then it is sealed in a steel containers or cylinders.
Yes, ma'am.
Also, it can be reprocessed. Fine.
Yes.
Okay, so now after this, we are having fission and the stars. Sorry, fusion and the stars. Let's talk about that. Okay, so let's continue without wasting time. What is a nuclear fusion reaction? Akshita, am I audible?
Yes, ma'am. You only the laptop got like hang, but I can
Yeah,
hear.
I know. Yeah, basically the one not is not behaving properly. It's okay.
Yes.
Fusion and stars I was talking about. So what is fusion? When two small nuclei give one big nuclei with the release of energy. Okay. Like here, I can take an example of hydrogen 2 1. Hydrogen 2 1 will give you helium 4 2 with the release of energy. So this is now nuclear fusion reaction which is carried out in the stars. Done? Now, so binding energy per nucleon versus the nucleon number. Have you seen the graph? I had shown you this many a time. Whereas
Yes, ma'am. Yes, ma'am. The one with the curved thing like that, ma'am.
sorry,
The graph would be like
yeah, here,
oh yeah, that one, yes.
yeah. So fine. So this is the graph. Here you can see that we see that the basically initially it is rising at the steeply. Then you will see that there are two more hydrogen helium atoms nuclei to get one helium atom. Okay. Then the helium nucleus would have more binding energy per nucleon, and the nucleus is more stable than the two fusing nuclei. Okay.
Yes,
See
ma'am.
here. So the energy for this is more energy of helium is more stabilized in comparison to hydrogen. Okay. So if we add up the total binding energy of the helium atom, it becomes 24 MeV. Okay. And the binding energy, then the two hydrogen nuclei, that means 24 MeV would be released. Done. So basically in one chain reaction, how much it is released? 24 MeV of energy. Done.
Yes, ma'am.
So each small nucleus has a positive charge, so they repel each other basically. Fine. So to make the nuclei come close together enough, a strong force of nuclear reaction is required, and that is also with a very high velocity. So for this to take place, the matter must be heated and the temperature should be very, very high. Like in the sun core, that is nearly about 13 million Kelvin. Okay.
Yes, ma'am.
Done. So now after this, the fusion reaction produces a lot of energy per unit mass of the fuel, and much research has been carried out to build a fusion reactor. Okay. So this is the particular theory of how to deal with the fusion reactions. Now after this, we are having astronomical unit. Let's talk about the astronomical unit. So basically the average distance between sun and earth. How much it is? So it is nearly 1.5 into 10 raised to 11 meters. Similarly, we have one light year also, which is 9.46 into 10 raised to 15 meters. So these are the two astronomical units that you have to take care in the mind. Also, we have one parsec, which we write it as 1 parsec like this, and this is 3.26 light years. Okay, let me tell you how does it work. So basically, 1 parsec angle is fine. So if we have 1 parsec of the length, and if I create it 1 arc second of the solid angle, let's say this is the distance is 1 AU. So here the distance in parsec is given over as 1 over angle in arc seconds. Done. So therefore, 1 parsec, it is nearly 3.26 light year. Understood? Fine.
Yes, ma'am.
Okay, so let me give you some of the examples that how do we calculate these. Check. So the sun is having 10 raised to 9 meters of the range, which is nearly, if I take it with the perspective of an ant, it is 1 millimeter. With the perspective of one pyramid, it is nearly 100 meter. And the solar system is having, if it is 10 raised to 14 meter, then one light day will be something like this. Okay, these are the comparisons, Akshita.
Yes, ma'am.
Are you getting?
Yes, ma'am.
Sun is 10 raised to 9 meters. How much it takes basically to round up a solar system? So in the solar system, it is in the center. Okay, so one light day is how much? 10 raised to 14 meter of the solar
Yes.
system. If I compare it with a galaxy, So 10 raised to 21 meter, that is 10 raised to 5 light years. If I compare it with galaxy clusters, 10 raised to 23 meters. If I compare it with the universe, 10 raised to 27 meters. Okay.
Yes, ma'am.
So it's just a comparison from low to high or small to bigger masses. Now let's talk about the next topic, and that is stellar parallax. Basically, the astronomers cannot measure the distances directly, and they use the angle subtended by the star from as the Earth moves around the sun. Okay, and they had mentioned this method as stellar parallax. Okay, let me show you how has it been done. So now listen over here.
Yes, ma'am.
What happens here is the biggest angle possible is measured. Okay, like how it is measured, that we need to see. Okay, let's shorten the time of explanation. Just give me a second. Check what is parallax. Is it understood or not,
Yes,
Akshita?
ma'am.
Sure.
Yes, ma'am. Yes, ma'am.
I want to wind it up in a short time. Okay. Okay, check. So tan theta is what? Sine over cos, or I should say perpendicular over base. Okay. So what they had used, this is perpendicular. Where is the base? Here it is, D. So perpendicular over base will give you hypotenuse. Done.
Yes, ma'am.
Sorry, perpendicular over base will give you tan theta. So perpendicular over base is done. So tan theta is what? 1 AU over D. So tan inverse of this particular value, that is, will give you D. Correct? And remember, theta we have to measure in radians.
Yes, ma'am.
Understood?
Yes,
Akshita,
ma'am.
understood?
Yes, ma'am.
Any doubts?
No, ma'am.
Sure?
Yes, ma'am.
Okay. So now apply this over here also. What happens is the sun is here, the earth is here, and the earth is here. So when we measure it from here, we get one angle. Okay, the horizontal is this and this is the angle. We get one angle. Now after 6 months, when the earth comes at position B, what happens? We measure the angle again for the same star, let's say orange star. So when it goes like this, again it will make the same angle, correct? So either
Yes,
you
ma'am.
measure this triangle or you measure this triangle, it will be same. So the earth and the sun distance is how much? 1 AU. The horizontal distance is how much? D. And this is the theta, obviously. This one is the theta. So how you will going to do it? You will say that your D is equal to 1 over P. Correct?
Yes, ma'am.
Okay. Any doubts in this?
No, ma'am.
Okay. So now after this, we are having EM radiation from star. So what happens is, as we are aware that the stars has been deduced by measuring the radiations that they emit. We have seen this in the quantum physics, right?
Yes,
That
ma'am.
how do we detect the number of elements in the star, right? So this radiation has two important pieces of information. Very first one is the intensity. And the second one is wavelength. Okay, so the intensity will give you brightness of the star and the wavelength will give you the color of the star, right?
Yes, ma'am.
So knowing the distance to a star, we can use the information to calculate the star's temperature, radius and amount of energy it releases per second. Understood? What we can
Yes.
calculate? We can calculate the star's radius, temperature and amount of energy it radiates per second. Understood?
Yes, ma'am.
Done?
Yes, ma'am.
Fine. So this is it for the day. Let's continue tomorrow. Only very small topic, that is the brightness and the luminosity of the stars is remaining. Okay. Already we have covered the absorption spectrum and your emission spectrum in quantum physics chapter. Okay. And this particular
Yes, ma'am.
thing is over now. Okay. Just one or two topics are remaining that I will cover tomorrow or day after tomorrow whenever you are having class. Just do let me know via your coordinator, Miss Sonia, and she will convey this to me. Done?
Yes, ma'am.
Okay. Bye, Akshita.
Bye, ma'am. Thank you, ma'am.
Bye-bye.